Okay, good morning. Last time we started on radiation from spherical shaped sources and sound propagation using description of sound propagation using spherical coordinates. Let me just go back and briefly review a couple of things before we continue in the same thing. First of all, let's look at the coordinates. Just describe the coordinates first. In Cartesian versus spherical coordinates. Let me see, let me do this. Don't write it yet. Let's take a position here. Point P. Okay. Point P on the XY plane is defined by phi or R. Okay, a distance R, and phi is on the XY plane. Theta here is an important angle if you take a look at it just for a moment. And when we say theta is a particular angle, what does it define? If you look at this, this is a theta angle that goes all the way around, okay? And so one needs to be careful about what that means. Theta is what we would call a polar angle, and phi is describes the azimuthal angle of the object. So theta, in fact, defines a circle. So it's an angle with respect to z, and it can move all the way around. And a particular point on the circle then is defined by phi. Okay? And of course the distance would be r itself. You see what I'm getting at? Okay. So when you have, let's say, a sphere, a spherical source, and on the spherical source you have, let's say, a circle. In other words, you have a sphere, you have a loudspeaker on it that's radiating. So the whole loudspeaker is itself a sphere, but you have a little diaphragm that's radiating. The way you would define its surface, if it's like this, let's do a cross-section of this. Then this would be the angle that only defines that, just around it. See, that would be z. So by saying theta, you're able to define this circle here, circle around here, sorry. You look puzzled. Yes? Let me see how I can... R gives you a distance. R and theta gives you an angle. If this were just 2 dimensions, okay, theta and R would give you a point. But in 3 dimension, it defines a circle at any place, because all you know is R and a theta with respect to this z-axis, so it could be anywhere. Okay, just going around. That's what I mean by that. Okay, now what we did, I'm just giving you a general outline of the spherical radiation. What we did was we used the wave equation. We wrote it in spherical coordinates. And the wave equation, then we did a separation of variables. This is sort of like a flow chart of what we have done. And one variable in the radial distance r, another in not angle theta, but cosine of angle theta, okay? Which we also wrote as, defined as eta. And then finally, angle phi. For each one of these, we have solutions. We haven't come to that yet, but this will give us spherical Bessel functions. Okay, spherical Bessel functions in terms of the standing waves, usually always non-dimensional argument, kr, wave number times the radial distance, and Neumann functions. And when you combine these together, we can have progressive waves that we will define. Hankel functions, spherical Hankel functions. So this is the r coordinates. The cosine theta, on the other hand, as we saw last time, gives us the Legendre functions. We came to this point and stopped last time. And phi was just harmonic functions in sine and cosine. Now, together, these two, I will go over these, but this is just a preliminary outline, the flow chart of how you go about these. Together, these give you the surface harmonics. Surface harmonics. And I'll explain that in a moment. Otherwise known as Laplace functions. Okay. When you look at these three coordinates, the second and third one together define the directivity, okay, directional characteristics on a sphere in a spherical coordinates, okay, only angle dependent. And the first one is a distance related object. Now, the solutions for these, we'll see, will have constant coefficients. And we will obtain the coefficients from some boundary condition. What is the boundary condition normally? Normally, vibration velocity of the surfaces, okay? And once we define these, we will have some, let's say, approximate solutions. We'll have, first of all, a general solution I will define. General solution of pressure, which will be a combination of the distance, theta, and phi angles. This will be the general solution. And then we'll have some special cases and approximations. For example, a uniformly expanding sphere, uniformly vibrating sphere, and uniformly oscillating sphere. And this means a sphere that just its surface uniformly oscillates, expands and contracts in all directions. Whereas a uniformly oscillating sphere would be oscillating as a solid back and forth like this. So its surface velocity would be maximum here and 0 here, because it would be moving back and forth, okay? Now, this is kind of the general view of where we will go, and what I'll do now is review what we have done briefly and continue to the general solution and do some special cases by the end of today's lecture. Any questions so far? Okay, so the wave equation in spherical coordinates you have seen this before, but I'm just going to write it again. So if there's a symmetry around the z-axis, then the dependence on phi will be 0. So this disappears. So you have a dependence only on Legendre functions and radius. So you can. This is it's just logical. You can follow this common sense. To solve this, as I mentioned, we do separation of variables. Where eta is cosine theta. And if we follow that, if we substitute this in the wave equation, we end up with a very nice compact form of the wave equation. What I want to point out here, just for a moment, let me have your attention just for a second, is the first set of expressions in the first bracket are all R-dependent. Okay, they just depend on the radius. And in the second one, you can see they depend on the angles, but both of the angles. So the dependence on the surface angles are interrelated. That's why, in some ways, we use these numbers together as surface harmonics, just the angular distribution. Together, they tell us which direction the pressure waves will be traveling. They define the directivity. All right. Right. And last time, I think we did this, we said, let us set, because they have to be able to satisfy this relationship, they need to be independently equal to certain constants. So we say, we set the first one, constant C, and then we also set the equation here to, let's see, what our phi square. Okay. Just this portion we're saying is equal to minus n squared. And we end up with now three sets of, let me just pull this down. Rewriting these, we have, first of all, the phi square n square, phi equals 0. Oops. That's a variable. This can also be written as the shorthand of cosine theta. Okay. You can see the relationship between the equations, the three variables, how they are coupled through the constants. And we saw the simplest expression is the first one. Are we following this? More or less? Okay. All right. Oh. The solution to the first one is sum of harmonic functions. And solution to the second one, as we saw last time, are Legendre functions. Let's see if I can express these. Now, one thing that's important for the Legendre functions, let me just write this, and this is where we had left last time. Yes, this relationship, which tells us that any cross product for different indices is zero. If they are the same by itself, then it has a finite value, which defines an orthogonal set of functions. And if you look at theta, okay, theta is cosine theta minus 1 to 1. What's cosine theta minus 1? (108 degrees, 90 degrees, 0 degrees? 180. So 0 to 180, from 0 to 180, okay? So that's the maximum values. Those are the maximum values it can take. So when you integrate it between those two, you have a finite value. So what does this mean? This means any surface shape in terms of theta, you can express it in terms of the Legendre functions. We'll use this later on. This is like Fourier transform, Fourier functions when you, or modal analysis, modal, any set of orthogonal functions. So Legendre functions are, they form a set of orthogonal functions. And let's see. So as a result, we can write any functions. Let's see. Let me move this. So since Legendre functions are orthogonal, we can express any function f eta or f cosine theta, right? Within range minus 1 to 1 in terms of, doesn't matter, yeah. Okay, and that means you take an ordinary function of eta, ordinary function of f cosine theta. We can now expand this in terms of the Legendre functions. And 0 to infinity, some constant coefficient times the function. How would you find the coefficients, Bm? Why don't you write, and let's discuss this for a second. This use of orthogonal functions to express a general function in the same set, with the same set, is a very helpful, very useful mathematical tool. If you haven't seen it, let's just spend a few minutes on it. What we're saying here is this, these Legendre functions, okay, of eta or cosine theta is an orthogonal set. So any function of theta, cosine theta, we can express it in terms of these components of this orthogonal set. So we say, okay, f eta then is equal to some constant Bm times function Pm, m from 0 to infinity. What are Bm? What are Bm? Bm are constant coefficients. How would you find it? Do you know? Does anybody know how to find Bm? Think about it. Say aloud what this means, and then the answer will come to you. Okay? What does this equation tell you? Emrullah, what does the equation tell you? What is f eta?
A function of cos theta.
Say again. F eta. What's f? All right. What's f? It's an arbitrary function. It's just a function of eta. That's it. Just some function of eta. Yeah, but what?
The arbitrary functions must be orthogonal. How?
No, f is not an orthogonal function. What is orthogonal? What is orthogonal? What are the orthogonal functions?
The time integral.
Not time integral. There's no time involved in this. These are the orthogonal functions. And we call these, this is the solution of this differential equation. See, this is a funny shaped differential equation. It is not like a second order differential equation that you're familiar with. Solution of this is just an ordinary sine, cosine harmonics. But when you look at this, this is, for example, this one. Well, it is also a second order. See, d square here, and but it's different than that. In fact, if eta were zero, this would be very similar to this. You see, very similar. Right? But it isn't. There's a dependence on what kind of value eta takes, because this is actually cannot be zero because p is a function of eta. Okay, eta cannot be zero, obviously. So it has a particular solution. Emullah, look up. These are orthogonal also, right? When you take their integral, similar to this, only they themselves will give you a finite value. Otherwise, cross products will be zero. So these are orthogonal. P, the solution of this is very orthogonal. Now, let's go back to this. Okay, let me ask the question again. What's f? Some arbitrary function of what? Exactly. And what does the rest of the equation say? Okay, let me write something else to see if you can make the connection. What did we do? Yes, if I have, let's say, f of alpha, I can express this. You'll agree with me, I hope, that am cosine m alpha plus bm sine m alpha. What is this called? Exactly, right? Any function of alpha I can express in terms of Fourier series, right? Or in this case, I can rewrite this and say this is cosine m alpha plus some sort of a phase angle. Now I have, what do I have here? I have constant coefficients. How would I find them? Where do I find the constant coefficients from? What helps me to find them? There's no boundary condition involved in this. Before you answer. Okay, this is just a function, and I'm representing the function in terms of Fourier series. What were we just talking about?
Integral limits help us, like from theta to minus.
And why are we doing that?
Because I think we are expressing the continuous function in terms of discrete function.
Well, yes and no. What we are doing is we are taking advantage of
Linearity.
orthogonality, not linearity, orthogonality, okay? And so let me just make it even simpler here. Let's say this is what I want to do, okay? How do I find AM? What would you do? You have never seen this, have you? You probably have, but you just don't remember. No? Maybe not? Okay, well, what you would do in this case is multiply both sides by cosine n phi. Okay, so if I do this, cosine n alpha, sorry, f alpha, and think about an expansion of this. We 0 cosine, oh, yeah, just a0 plus a1 cosine alpha plus a2 cosine 2 alpha, and so on. If I multiply both sides, I will write this in red for a moment, then this will be cosine n alpha, this will be cosine n alpha, cosine n alpha, and so on. And then integrate them over a limit. Alpha may be minus pi to pi, okay? Now, if the coefficients are different, okay, they're going to be 0. So the only thing that's going to give you a number here is when n is equal to m, just like the other one, okay, from orthogonality. This is how you find the coefficients of a Fourier series. So similar to that, and I didn't want to get into the Fourier series studies here, but similar to that, you do exactly the same thing. But, okay, let me just write this in an expanded form. Okay, this is what that's equivalent to. You expand this. Now, let's see, I want to evaluate B1. Okay, in that case, I would multiply both sides, P1 by P1 eta. And integrate. Minus 1 to 1. So far, so good? You're following what we're doing? Very simple. Now, what does this tell us? When they are different, the integral is 0. Right? When they're the same, integral is a given value. So, 0, 0, and all the others are 0, but this one, what is the value of this? You see, the value of this is 2 divided by 2 times 1 plus 1. That's what it is. Okay, now let's go over here. We have now This then gives us B1 times 2 over 3. And from here, since we do know what F eta is, you integrate this and you have the value of B1. And this is the way you use orthogonal functions. Anytime you have a set of orthogonal functions, you're able to use that, and it's a very, very powerful and important tool in expanding different functions. So I will write here the general expression for, finally, for Bm. Okay, before I start erasing, let's just go over this. First of all, do you have any questions? Do you understand everything perfectly well? Yes, no, maybe? If you have questions, this is a good time to review them. Let me, because there's something here that I need to point out again. Let me just start with the general outline of what we're doing. Let me pull this up. We have a general expression for wave equation in spherical coordinates. This describes propagation of waves in using just spherical coordinates, radial direction as well as angular distribution of these. Okay? So we apply separation of variables, which then gives us an equation in terms of these separated variables. Okay. If you look at here, we said these separations, the angular components will give us 1, Legendre functions, which you have just seen, and 2, harmonic functions, which are very straightforward. If you look at the harmonic functions, they define an angle on the xy plane. What does that also mean? It will also be the meridians on a sphere, okay? The longitudes, meridians. Whereas the polar coordinates will give you the parallels, okay? You change the angle, you have another parallel on the spherical surface. Together, they give you surface harmonics. We haven't come to it yet, we will. And then define the angular description of the sound source or sound propagation. Now here, when we substituted, we do have these new 3 different differential equations, and the equations are coupled to one another. In this case, for these theta dependence, we said it depends on n being the harmonics of the phi, okay, around the z-axis. We first solved for Legendre equations for n0. This is an important point, okay? Here, put here, for n0, meaning an axisymmetric solution, okay? And so these values that I just gave you a moment ago, these are all for, you don't see the number n. Okay, what is n? N is the couple to the variation around the z-axis. So these are in some ways axisymmetric. N0 means axisymmetric. And a lot of our problems are axisymmetric. The next thing I will do is just show you how Legendre functions can be expressed when n is not equal to 0. Okay? So when you don't have this axially symmetric case. Okay? I see you're very excited about all these. All right. Okay. So we use the orthogonality where now we know how to express an arbitrary function in terms of Bessel functions. Let me just briefly give you actually just the result when it's not orthogonal. Okay. For the case n is different than 0. Okay. Once again, just remember what n represents. If n is 0, this is completely symmetric about the z-axis. Okay? But when it is not symmetric, then we have, of course, the original equation, this right here. So we are interested in describing solutions for sound phenomena. Unique and continuous for values -1 eta +1. And I will not go through the details of this, but at the end, after some mathematical derivations, this Legendre functions that represent the solution for this n different than 0 is given as 1 eta square n over 2 The important thing to note here is non-symmetric Legendre functions are represented by symmetric solutions. Okay. Once you write that, let me explain what we mean by that. Two things before the break. Okay, one is solutions for N0. N0 meaning z-axis, it's axisymmetric. We have this expression for the solutions, and I will go over this just very briefly, and its property for the axisymmetric solution in terms of orthogonality. One. The second part of that is when it is not symmetric, we can express the asymmetric solutions in terms of symmetric solutions. That's the reason we first developed all the symmetric solutions, because we can very easily get these. Now, the second part of what I want to get at here is take a look at this. Okay, and see what that does for us. I think I can erase some of these. Let's just take a look at this expression. See, you're told this is a Legendre function, but do you have a sense? Do you have a feel for what that means? No, absolutely nothing, right? Okay, let's see what it means. Is there a way you can calculate these? What does it tell us? Remember, these equations always tell you something. Well, let's start with M0, shall we? Okay. M0 give me the values, please. 2 to the M.
1.
Yeah. Okay. 1 times, say again? 1. Okay, that's 1. And D0. This is no derivative, right? Exactly. So the first value, P0, is equal to 1. Sorry, the 0th value. So M equals 1. Now it's getting complicated. Okay. 2 to the 1. This is 1. Am I making a mistake? No, not yet. D over theta Okay, what does that give us? If you take a derivative of this, easy. You can see now it just comes out very easily, okay? And these will be all functions. You can do the second one, the third one. They will be all combinations of sine theta, cosine theta. Okay? But that particular combination is written like this in a compact form, and these are proven to be orthogonal set of numbers. I mean, this should not be a surprise to us because it is the angular distribution with respect to theta. Any questions?
I have a question about the term N times M.
Yes, that came from the derivation earlier. Actually, this the C, we set it to M times M plus 1. Okay, this is it came out in the derivation. What you do is you take, just like these, you expand these, make a substitution, and from there it comes out. I skipped a long derivation of this non-zero case because it's taking us into a very different direction. Okay, give you a 2-minute break or 5-minute break. All right.